Welcome to AP Chemistry. Recall that the internal energy of our chemical system represents the total kinetic energy within that system, and that any change that occurs in the internal energy of the system will be conserved as energy either moving into or out of that system. This is an extension of the first law of thermodynamics, which states that energy cannot be created or destroyed, that the energy of the entire universe is constant. Therefore, any change to the internal energy of the system can only occur by either work or heat, with work being kinetic energy of the particles in a given direction, and heat being kinetic energy of the particles in all directions. For our purposes, work in our gaseous chemical system comes in two forms: compression work or expansion work. Compression work represents kinetic energy being added to the chemical system by the gases being compressed by constant external pressure. Expansion work represents kinetic energy being removed from the chemical system by the gases being allowed to expand against a constant external pressure. In the example of a refrigerator, all four possible processes are utilized. Beginning with the compression of the refrigerant in the gaseous state, work is done upon the chemical system and its internal energy is increased. The compressed gas is then allowed to condense through coils in the back of the refrigerator. This exothermic process releases heat to the surroundings. The pressurized liquid is now allowed to expand against a valve, doing work against it, in order to become a depressurized liquid, which decreases its internal energy. Finally, the depressurized liquid is allowed to absorb heat from the environment inside the refrigerator, an endothermic process that increases the internal energy of the system, and the cycle begins all over again. In this unit, however, we will ultimately focus on enthalpy change for our chemical system. That is, the heat change per mole of process that will be given. In order for us to determine the exact amount of heat change that has occurred, we will need the experimental framework of calorimetry. A simple way to measure heat change is through the use of a coffee cup calorimeter. Here we can take an example in which we add a certain mass of cold water at a measured temperature to a certain mass of warm water at a measured temperature, and then after mixing them together, measure the resultant temperature. It should be understood that heat will migrate from the hotter to the cooler system until both systems are equalized. Since Q is equal to mc delta T, we can set Q lost equal to negative Q gained, and if any single variable is missing, we are able to work backward in order to solve it. If it was a hot metal that was added to the water, the setup would be much similar, with a slight modification of the metal's mass, metal's heat capacity, and its delta T. We should not be naive, however, about the true dispersion of heat. Most problems that you will encounter will state, assume no heat loss to the environment. But the truth is that there will be a significant loss, and in a true experimental setup, the calorimeter's heat capacity would have to be determined as well. The ultimate purpose, however, is to experimentally determine the heat change for a given chemical process. Take the dissolving of sodium chloride in water. If we know the initial amount added of sodium chloride added to the water, we should be able to determine the final temperature of the water if we know the change in enthalpy of that process. And using the experimental setup, we can work backwards to determine that value in heat change per mole associated with any given process. We should note that many salts vary in being either endothermic or exothermic in their dissolving process, which serve as the basis for many heat or cold packs. To conclude our discussion of enthalpy, which we introduced several units ago, we will reconsider its use as a state function. Ultimately, the heat energy associated with any given process can be used algebraically, just like the moles in a given reaction. If we are given a number of associated processes, we can rearrange them algebraically and determine the enthalpy change for any unknown process. Watch carefully in the next set of slides how this can be done for the example below. You should note that the enthalpy of combustion, like the enthalpy of detonation, is the heat energy change associated with only 1 mole of fuel undergoing combustion. Finally, just like we were able to previously determine the enthalpy of formation for any ionic compound, something we did several units ago, we can acquire tables for the formation of all types of compounds, and then use them algebraically to solve for any given reaction. These values given to us in tables are called standard enthalpies, and are measured at 25 degrees Celsius and at 1 atm of pressure or at 1 molar concentration. You will note that the enthalpy change for all pure elements in their natural state at 25 degrees Celsius and 1 atm, or 1 molar, is always 0. This is because there is no heat change associated to form them at those conditions, for they are already given to us in their natural state. With these values, we can algebraically determine the enthalpy change for any reaction system. The enthalpies of formation of the reactants, however, will need to be reversed, since we are not forming them. The signs of the products, however, since we are forming them, will remain the same. Till next time we consider the mysteries of the absolute, Crip.